All right, so we did get to this box yesterday to memorize. The derivative of the natural log of x was 1 over x. Memorize that. And if I add absolute values around the x, does it matter? No, they go away. And we saw why. We saw why graphically, and we saw why algebraically with the piecewise decomposition. And then the chain rule built right in. The natural log of u is 1 over u times u prime. And let's add this one more here. What's the derivative with respect to x of the natural log of the absolute value of u? Well, it would be 1 over u times u prime. Same thing. So it doesn't matter if the absolute values are just around the x or around like a function of x, like sine of x or whatever. They go away when you take the derivative. They go away when you take the derivative. All right, so let's try example 8. Find the derivative of each of the following. Now, it is kind of nice to get this reminder to simplify early and often. We now are going to add a little addendum to the end of that. Simplify early and often, comma, not period, or exclamation point, perhaps is a better way to say it. Especially when you have logs. Why would you want to remember to simplify when you have logs? They make molehills out of mountains. Yeah, very good, very good. All right, so here we are on example 8a. h of x is cosine of ln of x. So this is the chain rule, right? We walk up, we see cosine. So the left side becomes h prime of x. What is cosine of blob's derivative? Negative sine of the blob. Yep. Times the derivative of the blob. What's the derivative of ln of x? 1 over x. Yeah. And now if we simplify that, that's negative sine of the natural log of x all over x. So that one didn't require any simplifying in the beginning. Okay, you'll know to simplify because log of products become sums, log of quotients become differences, and exponents can come out front. So that's part A. Pretty easy, right? Chain rule, cosine rule. All right, here we go. The natural log of 1 plus ln of x. Now, in the spirit of simplifying early and often, especially when we have logs, should we distribute right there and call it the natural log of 1 plus the natural log of the natural log of x? Because the natural log of 1, after all, is 0. That would just become the natural log of the natural log of x. Can we do that? Should we do that? Does that work? No. We cannot take a log and distribute it inside its own argument. That does not work. No, no. So, yeah, got it? Got it? Good. All right, so let's just not erase that. Let's just keep that as a record of things not to do, okay? Let's add over here, let's add drugs, okay? Okay, another list of things not to do. Okay. So, we jump in. What's the derivative of the left side? dy dx. Can you use y prime? Someone asked me, can we use y prime? You can. But remember, every time you write out dy dx, you're sending a tribute to Leibniz, who didn't get credit in his own day. And I think T-Mobile also donates $1 to flood relief every time you use dy dx. Okay. So on the right side, we have the natural log of blob. What's the derivative of the natural log of blob?
1 over the blob.
1 over the blob. Good, 1 over the blob. Times the chain rule, the derivative of the blob. What's the derivative of 1 plus ln of x? 1 over x. 0 plus 1 over x, or just 1 over x. Excellent. So now we'll clean it up, and we get 1 over x quantity, 1 plus ln of x. And that's factored, so we'd prefer it factored to distributed. So there you go. Easy, easy, right? We just have a new rule, and we're incorporating it into the old rules and our old skills. All right. This one's called f of u. F of u, right? The of is very important. F of u. Go ahead and take about 20 seconds and see if you can chew on that one. All right, let's try it out. F prime of u is going to be the natural log of blob, right? So that's 1 over the blob, all times the derivative of the blob, which is a chain rule with a Hody high built into it.
Let's not do that.
Right, f of u.
Can't we
No way.
Put that into as argument and bring the exponent to the front the log.
That's exactly what we're going to do. We did not simplify early and often, so let's do that. Logs are going to be especially useful to simplify expressions when you have multiple factors that are either multiplied or divided, and or exponents, which, remember, radicals are exponents in disguise, rational exponents. So yes, f of u can become more palatable if you simply write it as 3u plus 2 over 3u minus 2 to the 1/2 power. Now, where can the 1/2 go? Tell it where to go. Out front. All right. So you get f of u equals 1/2 the natural log of the quantity 3u plus 2 over 3u minus 2. Now, if that was all we did, that would be a huge help. We got rid of the whole chain rule thing, right? We turned it into a 1/2 scalar multiple that just now goes along for the ride. But wait, there's more, right? Call now within the next 30 seconds at 1:30 in the morning. All the commercials when they play, it's like they're always giving you 30 seconds after the commercial to order to get the bonus Ginsu knife. Right. We now have the natural log of the quotient. And logs turn quotients into differences, subtractions, and right. So subtractioners things. Now be careful with the 1/2. It's out front. So if you want to put a beefy purple bracket, that's going to be natural log of the numerator minus natural log of the denominator. And whether or not you want to distribute the 1/2 to each term, that is entirely up to you. But you do have to account for it in the correct way. Now we can distribute the log inside the arguments, right? No, we don't do that. We just saw that. Okay. That's about as simplified as it can get. We haven't done any calculus yet, but we have made definitely a molehill out of a mountain, right? And molehills are considerably smaller than mountains. No one ever claims they were the first one to climb a molehill, right? Now what? Derivative, right? So f of u, no, f prime of u. 1/2 goes along for the ride. Constant multiples go along for the ride. So just keep them there in the front. And now I have two terms. That's like two smaller individual baby problems, right? What's the derivative of the natural log of blob? 1 over the blob times the derivative of the blob, which is 3. Hey, you know what you could do just off to the side here? Since the derivative with respect to x of the natural log of u is always 1 over u times u prime, there's always a 1 in the top. You could just do the shortcut rule and say it's u prime over u if you want. U prime over u, or 1 over u times u prime. So knowing that, you could have called it 3 over 3u plus 2. But I'm just going to leave it like this. I'm just giving you the option. 1 over blob times the derivative of the blob, minus, we do it again in the second term. The derivative of the natural log of blob is again 1 over the blob times the derivative of the blob, which is 3. Wow, that was totally worth it. Yeah, you remember the bad attitude we had originally and the vulgarities that were almost escaping our mouth when we were trying to do it without simplifying? Yeah, no, this was almost like fun and pleasurable to do it this way. Thank you, logs. Thank you. There's no logs in your final answer. Oh, well. Let's go ahead and distribute now. I'll distribute the 1/2 and put the 3 in the top. You get 1 over, or 3 over, sorry, 2 times 3u plus 2 minus 3 over 2, 3u minus 2. So instead of distributing the 1/2, you could have actually factored out the 3 from both of them and gone from there. But from here, you could get a common denominator if you want. 3u plus 2 and 3u minus 2 are conjugates. So if we did proceed in getting into a single term, it would probably be pretty nifty. But I'm not going to do that. I want you to realize that when you have logs with multiple exponents, multiple factors, use the properties of logs before you take the derivative. And it makes life so much easier, so much more enjoyable, okay, when you don't do drugs. Did you see that President Trump, declared a state of national emergency yesterday with the opioid crisis, right? So drugs don't have to be illicit drugs. They could be licit, okay, if you abuse them. So, what if the base of the log is not e, right? I know that's what you're saying. Yeah, this is all great and all, Ms. Scorpy, but, you know, There's other logs out there besides the natural log, right? We got unnatural logs like log base 11 and other things like that. What are you going to do if it's like in general log base B, like log base 7 or log base 5, you know? Log base 10. What if we're in science class and we need the derivative? Well, what can we do if the base is not to our liking? There is a formula called the change of base formula. Right. Which in Ireland they call the change of base formula. All right. What base do we know how to differentiate? E. So I'm going to go ahead and convert log base B of x to log base E. This is not calculus or witchcraft, all right? The way you change the base is you take the natural log of the argument over the natural log of the base. Remember that from pre-cal? You can kind of see that the argument is a little bit higher than the base. The base is written a little bit lower as a subscript, bless you, than the argument. Bless you, base, bless you. The B goes in the bottom, and the X goes in the top. Now, that's natural log. If you don't like natural log, you could say it's log base 7 of X over log base 7 of B. You could change it to any base you want, so long it's log of the argument over log of the old base. We like the natural log because we know how to take its derivative. So now if I simply rewrite this so I don't have to use the Hody-High rule, as fun as it is, B is a constant, so the natural log of B is a constant, so 1 over the natural log of B is a constant, right? And now I have a constant times the natural log of X. Now I can take the derivative of both sides with respect to X, and constant multiples go along for the ride, don't they? So it's 1 over the natural log of B times the derivative of ln of X, which is 1 over X. And so now we have this rule. The derivative with respect to X of log base B of X is 1 over X natural log of B. So remember, if it was exponential, the derivative of any exponential function, like e to the x, was itself, but then times the natural log of the base. If it's a log function, base B, just like the natural log of x, it's going to be 1 over x, just like natural log, or 1 over blob. But instead of multiplying by the natural log of the base, we're going to what? Divide by the natural log of the base. And that kind of makes sense, because multiplication and division are what's? Inverse operations, just like exponentiating and logarithmicating. Does that sound right? Logging, right. Yeah, logging. Okay, so you got that, right? 1 over x, or 1 over blob, and then divide by the natural log of the base, or multiply it in the denominator. Let's try it out. Let's try it out with the natural log of x. It should be 1 over x, and in the denominator times the natural log of the base. What's the base of the natural log? E. What's the natural log of e? 1. So the natural log is the only one that's just 1 over x. It's not its own grandpa, but I guess it's related to its grandpa. Everything else is going to have a natural log of a base in the denominator, okay, with the 1 over blob. So here we go. Memorize. Derivative of the natural log, or log base b of x, is 1 over x, natural log of b. What if the absolute value were there? Same story, right? It's still just 1 over x, ln of the base. And if you got the composite function, log base b of blob, it's 1 over blob natural log of base times blob prime, times the derivative of blob. So that has the chain rule built into the rule. All right, let's try it out on example 10. If f of x is log base 3 of 5 minus x to the fourth quantity squared, find f prime of x. All right, simplify early and often, especially when we have logs. Do we have logs? We do. Can I simplify it all? I can. What can I do? Can I bring the 2 out to the front? I cannot, because that 2 is not squaring the argument. That's the only time you can bring it out front, if it's on the argument. It's squaring the logs. That's like a log times log. So the 2 does not come out front. So the only thing you would be able to simplify would be 5 minus x to the fourth, and there's really nothing we can do with that because it's two terms. If there were like another exponent in here like of 3, then you could bring the 3 out in front or something like that. But there's nothing. There's just a 1. So now it's just a chain rule. Walk up to the problem, and all you notice is blob squared. So the 2 does come out front, but on the derivative step, right? By the power rule. It's 2 blob to the first. And then there's the blob. Times. Oh boy, now I come in one layer, and I spy a log base 3. What's the derivative of any log of blob? 1 over the blob. 1 over 5 minus x to the fourth. But now, before I leave, in the denominator, I need to multiply by the natural log of 3. Good. So that takes care of the log base 3 layer. And now, times the chain rule, again, the derivative of 5 minus 4x to the fourth, negative 4x cubed. Yeah. And there is the natural log of 3. I'm not going to clean that up. You can if you want. You'd have a negative 8x cubed log over, bless you. Yeah. Okay. Sweet. All right. We are rounding third base and heading home, which I hope the Astros do a lot tonight while the ball is still in the outfield. Game 3 tonight at home. All right. So what we did up here on part C on f of u was we took the derivative of a function that was a log function, and we used the properties of logs to help us simplify it prior to differentiating it. What we are now going to learn is something called logarithmic differentiation, which is not the same as taking the derivative of a log function. This is a process, logarithmic differentiation, or RATCON for short. No, sorry, log diff. Log diff for short. That's better. Log diff. So what this technique involves is it involves taking the log of both sides of a function, taking the natural log of both sides of a function prior to differentiating. And when you do that, now you're going to make it implicit. So you're going to have to use implicit differentiation. But if you are finding that you need to simplify a grotesque expression or function, it has lots of factors, lots of quotients, lots of radicals, lots of exponents, a situation where a log would help remedy that, and there's not one there, you could introduce a log to both sides and use the properties of logs, okay? So let's take a look at example 11. Before this section, if I asked you to take the derivative of y with respect to x, you probably would have done it, right? Because y'all are excellent students, but you would have been like, nothing, right? Probably, right? Because look, it's a ho-d high rule, piece of cake, ho, but what does d high involve? A product rule with a chain rule. Okay, so that's d high. Minus high, d ho, are you kidding me? Are you kidding me? And then over ho squared, I don't think so. I don't think so. This is a function with no logs in it, right? But it's got 1, 2, 3, 4 factors. And on those factors, we have 1, 2, 3, 4 exponents, right? Would logs help here? To simplify? To make the molehills out of this mountain? Yes, they would. But we don't have it. So the process of logarithmic differentiation is as follows. We are going to take the natural log of both sides. You take the natural log of both sides. Now, remember, when you've done that, you have changed the function. You have now made it an implicit function. But it's going to make the derivative a lot easier to take, even though you have to do it implicitly. All right, so if you don't want to rewrite this on the right-hand side, you can go straight to this next step. The whole purpose of having the log there is to expand it out. So let's, if you do rewrite it, let's go ahead and rewrite this square root of x plus 1 cubed as x plus 1 to the 3/2 power, okay? So now we're going to expand it in one fell swoop. Here's how it works. Every factor in the numerator gets its own log, and they're added together. Every factor in the denominator gets its own log, but they're subtracted from each other, And where do the exponents go in each term? Out front, okay? So, here we go. It's going to become the natural log of e to the x. But look, with notability, you can actually grab the x and go, slide it to the front. That's fun. Plus, yes, you could also just call that x right away. Absolutely. Plus, leave a little space. The natural log of x squared plus 2 to the 4th power. Lasso it with scissors. There it goes. Now we're in the denominator. So minus, leave a little space. The natural log of x plus 1 to the 3/2 power. Grab the scissors. And on the last one, you could just say minus 2 natural log of x squared plus 3. Right? You don't have to do the blip every time. You just know that the exponents on each term are going to come out front. Now, if you want that to be the next line after here, I get it. There's really no reason to rewrite the function unless you feel like it helps you, like writing the square root of x cubed as x plus 1 to the 3/2, if that helps. But now, we haven't done any calculus yet, have we? And we can even simplify this even more, because the natural log of e is equal to what? 1. So that's just x. And again, someone was saying, couldn't we just, the natural log of e to the blob is just the blob. So now, we have 1, 2, 3, 4 terms on the left, on the right, instead of 4 factors. And we have 4 constant multiples instead of 4 exponents. Much easier. So now we'll take the derivative of both sides with respect to x. Now here's another thing that we can do. Remember I told you with implicit we put d dx of both sides? You can still do that. Or you can now say d dx colon, which means I'm taking the derivative right here. Okay? Look out, here I come. It saves a little bit of writing. What would be the derivative of the natural log of y then? 1 over y times the chain rule, dy dx. Good. Good, good, good. Equals, what's the derivative of x? 1. Sweet. Plus, 4 goes along for the ride. What's the derivative of the natural log of blob? 1 over the blob times the derivative of the blob. What's the derivative of x squared plus 2? 2x. So there's where u prime over u could be helpful. The natural log of x squared plus 2 is the derivative of that 2x over itself. If you want to do it that way, I'm going to do it that way. You can still do 1 over blob times blob prime. Minus 3/2. What's the derivative of the natural log of x plus 1? Well, it's 1 over x plus 1 times the derivative of x plus 1, which is still 1. And then minus 2 goes along for the ride. The derivative of the natural log of x squared plus 3 is 1 over x squared plus 3 times the 2x, which I'll throw into the numerator. Are we done? No, because remember, anytime we did implicit differentiation, after the calculus came the algebra. We have to solve for dy dx, which means we have to expand it all out, get all of our dy dx terms together on one side, factor it out, and then divide through. Hey, we already have dy dx isolated on the left. So all we have to do to solve for dy dx is multiply both sides by what? By y. So it's going to do, I'm not going to show that. dy dx is left on the left, we multiply by y, and then we're going to get all of this stuff, 1 plus. Now you can go through and simplify. I'm going to call that an 8x over x squared plus 2, minus 3 over 2 quantity x plus 1, minus 4x over x squared plus 3 times y. Now, guess what? Something looks out of place on the right-hand side, right? It started as a function of x. It's a party of x's, except now y is on the outside knocking. Can I come in? No. No. You don't want to put a y there. Not that it's wrong. What was y originally equal to? That whole thing. So guess what you're going to write? You're going to write that whole thing one more time. Yeah. Good riddance. This is your last attention you're ever getting from me, you stupid, big, ugly function. Easy, gosh. There you go. All right. So there it is. Notice that when you use log diff was not required here, was it? We kind of used log diff. We took the natural log of both sides to take advantage of the properties of logs. It wasn't required, but it sure made it easy. Notice when you use log diff then, it's going to always kind of have this look at the end. It's going to have several terms, maybe sometimes just one term, but generally you're going to have a couple of terms, and then all of that is going to be multiplied by the original ugly thing that you didn't want to differentiate. He's going to be a visible factor in your final answer. And that can help you kind of narrow down a search on a multiple choice. Okay? So the process, again, of introducing the log into the problem to take advantage of its properties before you differentiate is called what? Log diff, logarithmic differentiation. And it is not required in this case. It was just an option. Okay? If you were doing it the other way, you're probably still working. Good. All right, let's look at this guy. The derivative with respect to x of sine of x raised to the cosine of x power. Is this exponential? It has a variable in the exponent. But it's only exponential if the variable's in the exponent and it's a numeric base. Do we have a numeric base? No, we have a variable base. Is it a sine rule? No, because sine rules have to have numeric exponents. This one has a variable exponent. This is a hybrid. This is something of the form function of x raised to the function of x power. You have a variable raised to a variable power. It's a hybrid. Guess how you're going to take the derivative of these hybrid types of functions? Log diff. And in this case, it's not an option. It's required. So there's really only two times you have to use log diff. When it's a variable raised to a variable power, and when the instructions say use log diff. Okay? Otherwise, you have it in your back pocket as a tool, as the ace in the hole, if you will. All right? Now, this is the verb format. To take the log of both sides, we need to have a what? We need to have both sides. We need an equation, right? We need an equation. So if it's the verb format, your first step is to actually say, let y equal sine of x, cosine of x. You have to take a step back and say, hey, wait a minute. Okay, now I have an equation. Now I have two sides. I'm after dy dx. Once you say y equals, you're after, in the end, dy dx. Okay? So now we could take the natural log of both sides. So this becomes the natural log of sine of x. And, of course, what happens to the cosine? Comes out front. That is why log diff works. It's no longer a hybrid. By the log being there, you bring it down onto the ground floor, and now it just becomes a product rule on the right. But it is implicit now. So rather than rewrite it d dx in front of both sides, we'll just put d dx colon. That's not dy dx, is it? It's d dx. It means I am taking the derivative with respect to x of that, and it follows on this line. So natural log of y becomes 1 over y, dy dx. Product rule. What's the derivative of cosine? Negative sine. Good. And then the other one we just rewrite. Natural log of sine of x. Plus cosine of x goes along for the ride, times the derivative of the natural log of sine. The derivative of natural log of sine is 1 over sine times the derivative of sine, which is cosine. So either off to the side or in the numerator. Wow, good eye. Yeah, good eye. Now we just have to solve for dy dx by multiplying both sides by y. So I'll put my beefy plum brackets, and we get negative sine of x times the natural log of sine of x. And you have a couple of ways to simplify that last term. You could call it cosine squared over sine of x, but that puts it as a quotient. You could just call it cosine over sine cotangent. And so now it's cosine x cotangent of x. And then times y. Now here's where you really don't want to put y, because y wasn't even part of the original problem. You're going to put what you called y, which is sine of x, to the cosine of x power. See that? So once again, you have the very distinctive look of having a couple of terms times the original expression or the original function you're trying to differentiate. That's log diff. Don't forget to multiply both sides by y at the end, because there will be answer choices that are exactly the same but without the y as that visible external factor, which it should be there if you use log diff. All right, so when is log diff required? When you're told to, or when you have a Hybrid, variable to the variable power. Okay, when can you use it? Whenever you want to. Yeah. It's really nice. It behooves you to use it in situations such as this, when you have multiple factors and multiple exponents. But it works all the time. It works all the time. So if you want to use log diff for every single problem that you ever encounter for the derivative, it'll work. For example, example 12. If y equals x squared, find dy dx using log diff. I can't just put 2x down? No. Nor can you put y prime equals 2x down, which is what you meant to say. We're going to use log diff, all right? I'm going to take the natural log of the left and the natural log of the right. And look, that 2, that arduous, cumbersome 2 on the x, it now slides to the front as a constant multiple. Yeah, he is. Yeah, I better make his self-confidence a little bit bigger. I'll put him on top. There you go. Now he's up higher. Feels better. Okay. Now we're going to take the derivative with respect to x. All right, with respect to x implicitly. So the left side becomes 1 over y times the chain rule dy dx. This becomes 2 times the derivative of the natural log of x is 1 over x. Cool. And now I'll solve for dy dx. It ends up being 2y over x. 2y over x. But, remember, we started as a function of x. So now I'm going to substitute. What is y actually equal to? X squared. So let's substitute it in. So dy dx is equal to 2x squared over x, which, by the way, if you divide out one of your x's, gives you 2x. And it works. Wow. This is the scenic Sunday version, Sunday drive version. So if you ever find yourself doing calculus on a Sunday, maybe use log diff, more scenic. Okay, it's time to relax and just enjoy the view. Ooh, look at that view. Okay, so log diff works any and all times, but it really only makes sense on non-Sundays when you have expressions that have lots of factors and or lots of exponents. Okay, logs do a great job of taming that. Bonus. Other uses for logs. Coffee tables. Planters. Look at that one. Planters. That's pretty. Placemats. Logs sliced real thin. And trees. You make trees out of logs. We're done.